Okay, welcome back to the View Dependent podcast, where we speak to industry leaders, researchers, and creatives operating in the world of hyperreal 3D, including methods like radiance fields. And with radiance fields, there's been, without exaggeration, no paper that has created such impact as 3D Gaussian splatting did last year. When you take a look at the top cited papers of 2023, number 17 was Google's Gemini, and just two places below that at number 19 was 3D Gaussian splatting. And today, we're really, really honored to have one of the two co-first authors of Gaussian splatting with us, Bernhard Kerbl. So thank you so much for coming on the show today, and we're really excited to have you here.
Thank you so much for having me, and also thank you so much for taking so much care and really getting the details correctly, saying a impactful paper of that year specifically, and also co-first author. I really appreciate that you're taking so much care in making sure these things are on point. That's really really nice.
Yeah, also from my side, welcome. I'm really happy to have you here.
Mhm.
It was a wild ride since last year. Many things happened, and I think there are also many things which we will see in the future based on your work. And so it's really amazing to have one of the first authors here and talk with you about 3D conscious aesthetic. Thank you very much.
Thank you.
Yeah, and so I kind of want to just get started straight away and ask, how did you get started in the world of computer science? Did you always want to be a researcher? What kind of prompted your initial journey into this world?
So I actually started with computer science somewhat late. Like the real computer science, I really only started at university. So before that, I was playing around with all kinds of 3D authoring tools, but more from the consumer side, never really from the developer side. So making small 3D worlds, making small 3D models, making some low poly workless creation, and these kinds of things. Um, and then actually, when I started my education at the Graz University of Technology, at some point, I actually discovered that I like programming. It just makes sense to me. And then that led into further studies in a master's for computer science and so specifically software engineering. And out of the subjects there, basically the one that was most rewarding was the one that give you a visual result or basically a visual output for the work that you put in. So pretty early, I was tending towards computer graphics and visual computing, and yeah, I found some very inspiring personalities there. Like for instance, Dieter Schmalstieg and Bernhard Kerbl and Markus Steinberger, who were all at this time at TU Graz, basically leading a force of high performance graphics research and pushing really into that direction. And yeah, I felt pretty much at home there. So I kept going into this direction and started out towards real time graphics and high performance graphics research, which I guess is the core of my scientific career.
What were the first topics you were doing research on? So more specifically.
So I think I've dabbled at this point in a wide variety of topics. So the very first topic that I did was on that was a little bit in the realm of medical visualization. So different ways for users to interact with medical data, which I found really really quite interesting. But then basically it being interactive. But then we very quickly moved on to really nitty gritty low level solutions that are at the algorithmic level. So where basically you have some sort of problem how to handle, in a very abstract way, how to handle data on the graphics processing unit efficiently. Basically, you can think of this as making tools similar to a sorting algorithm, but for basically taking arbitrary workloads, like for instance, the ones that come up in rendering, and processing them very efficiently on the GPU and then producing the outputs again very efficiently. So working at the low level of making these things work, like twiddling bits and optimizing individual instructions was actually one of my first projects. Yeah.
And when you talk about having an interest in visual based graphics too, what was your thoughts when you first saw like NeRF, or when did you first come across it?
Oh, so my first impression when I saw NeRF was I was like really impressed. I was also really intimidated because coming from computer graphics, I always looked at computer vision as, that's the big math stuff. That's the part that I want to stay a little away from. But then over time, the more I got familiar with it, I basically figured out that all of this that really doesn't need to be so scary. Yeah. So from the computer graphics side, we usually approach things, especially in real-time graphics, from a pragmatic point of view and a very discrete point of view. Whereas in computer vision, things tend to be more continuous, more abstract, more generalizable, and that can seem like very lofty and a little bit intimidating if you're coming from the pragmatic computer graphics side. But I think there's really nothing to be scared of, and I think those two can really very much work hand in hand for great results.
Was this kind of inspiration for your following up work? So did NeRFs inspire you?
Yeah, definitely. So I basically, when I joined the group of George Tredakis, where we did this research in France. So this is part of the INRIA network, so the Institut National de Recherche en Informatique et Automatique, which is a national research group which has locations all over France. And basically, I joined them because I knew they were working on radiance fields, and I wanted to get my hands dirty, like in a hands-on project. So I basically went there to learn about radiance fields. That was my initial intention.
And when you were there, you actually worked on a paper called NeRF Shop, and like speak of like intimidating things. Like how was it kind of taking into consideration like making NeRFs editable?
Sure. So that was where I basically saw, or basically had the experience that, well, there's a good combination of both worlds, right? Uh, the people who understood very well what NeRF is doing and all the differential behavior were having a harder time understanding the intricate and very well designed system that is instant NGP and its implementation with efficient CUDA kernels. Yeah? And in order to make something interesting happen, those two sides need to come together. So for me, looking at, for instance, those CUDA kernels, those highly optimized and very nice code sections, wasn't that hard. And I could see that other people's were benefiting from me being able to do something there, and at the same time, them providing ideas for high-level solutions for using these highly efficient functions to make the editing happen. Because in editing, things need to be interactive. You cannot wait 10 seconds for your dragging operation to actually go through, right? That would be a pain. If you drag something, then maybe 10 seconds later it happens. That's always a hassle. So you need those high performance solutions, as for instance given by instant NGP, to get that interactivity that we were after.
Was this also inspirational for your following up work? Because if NeRFs are really hard to edit, there might be a better solution to come up with.
No, so I can't say that it was. It could have been, but it wasn't. With the NeRF shop, we had an interesting challenge of having this less transparent, less elucidating representation of the NeRF, which is still to me a little bit of a black box, being editable. And with the 3D Gaussian Splatting, which came after, being easy to edit, that was honestly a side product. That is not what we were after initially.
And while you were at then INRIA in that group, is that where you first met George Kopanis, or how did you kind of start get linked up with him?
Yes, no, that's when I first met George Kopanis, or Yorgos Kopanis. That's also where I met George Tredakis for the first time, and it was also the first project where I worked with Thomas Leinkühler, who is at MPI in Saarbrücken, leading a group there. So very, very, very capable team.
And so now that you have this like, team all working together and such, how did the actual underlying foundation of 3D Gaussian splatting come about?
So Yorgos Kopanis started his PhD, I don't know if it was 2020, I would need to look that up. I think around 2020. And he has I think most of his PhD work has been on these point-based representations. Like he really wanted to bring them back. There was some back and forth with George Stratakis as well. And I think Yorgos Kopanas at the end, or in the end, basically convinced George that, yes, this point-based representation is really gonna make a change. It's gonna make a difference. We should definitely go for it. So George's, this is a little bit complicated, right? Both of them are George. That's why I call Yorgos, and I call George, right? So George really wanted to have the solution where we say we have input images, which are casually taken by a camera with decent settings. Like it's not a professional camera, it's a camera that anybody can wield. And you get some recordings, and from this you reconstruct the scene, and it is really fast, and it looks really photorealistic. And I think he said he always wanted to have a reconstruction of Nice. Like George very consciously chose the south of France as his base of operation, and he loves Nice. And he said like his dream would be at the end that somebody, like any casual user, can walk their home city, like for instance Nice, and make a realistic, photorealistic construction of it, and then just explore it and have all these extremely nice corners and places and nooks and crannies to show off to everybody else in 3D. And sorry, I'm derailing a little bit, but long story short, so George's dream was to have this image-based reconstruction work flawlessly, and Yorgos said, let's do it point-based. And he had done 2 prior works before we started on 3D Gaussian Splatting, and those 2 prior works very much set the stage. They could do a lot of impressive things. They also, in some cases, had like really, really outstanding quality, but it was painfully slow. Yeah, and that is where we came in, where we said we have the idea, the core idea. Now let's risk it, and let's say, what if we can reduce the requirements tremendously, reduce the requirements of what needs to go into the process, and then also reduce the processing time, and then we would have something that would like really make weight. And that was our goal.
So you started pretty much working on the rasterizer first. So when it's a goal to rasterize a point cloud, even if it's like a very sparse one in the first place.
Yeah.
Oh, yeah, this third. Okay.
So I started with so Yorgos had libraries for rasterization, and I basically started with them as inspiration and with them as a foundation, and then tried to really like figure out, okay, in this whole system, what is taking the most amount of time, what is taking the most amount of pre-processing, and what's the actual payoff. And then basically just started strategically trimming fat and figuring out ways to make each individual part develop more efficiently. And of course, always in collaboration with Yorgos, who knew this system already really, really well.
Mm-hmm. So then you got it working at one point, I guess.
Mm-hmm.
But then it was like you have, okay, a sparse point cloud, and there's nothing happened, right? So you needed something like an addition mechanism. Was it like in this order?
Not like we were always certain that we need a higher number of Gaussians than those SFM points. That was always clear to us. And I think like from the beginning, we knew somehow this kind of densification of Gaussians needs to happen. And it probably needs to happen progressively. So this was basically part of our schedule from the start.
And so were there any like really core challenges, that you encountered upfront where, you're saying like, is this going to work, or is this actually going to be, a fundamentally new representation?
So the thing is, we actually, like the initial plan was to go for what is now the hierarchical 3D Gaussian representation directly.
Yeah.
That is what we were actually after, because we were all thinking about, hey, we can make this scale really well, yeah, in the end, if we do it nicely. And like around Christmas, Yorgos Kopanas was running the usual metrics and the usual evaluations, and he was like, hold on, we have something here. Like we have really, really good quality, actually. Like in addition, like even without all this hierarchical stuff and scaling up stuff, we're getting really nice quality numbers in a very low time span. And that is where we actually consider, okay, maybe we should just submit this, right, to the SIGGRAPH conference. That was not our initial intention, but that's how it, in the end, actually turned out. And that's what we did.
I can imagine there's like a lot of frustrating work, especially if you want to get the gradients right at the beginning, right? And you really don't have any reference where you can measure against, other than you have like a numerical
Yeah.
verification, right?
So there we basically benefited from Yorgo's very disciplined and intricate work that he had done on his previous projects. Yeah. So we could always compare against his rasterizer, which he very meticulously had tested in all kinds of little toy cases. So if we had like a certain number of Gaussians to differentiably render after you project them into 2D Gaussians, we were always able to compare what we produce in terms of gradients with his gradients. And that was super, super helpful.
And what was like the general time frame from like start to finish on when this idea first started to be conceived to, the actual final this works?
So, I mean, if you see it as a series of incremental steps from the very beginning, where Yorgos started with the neural point-based rendering, or PBNR, point-based neural rendering, actually, I guess it would be 2.5 years, all in all, taking all the experiences together. But this particular project where we said, okay, this will be a submission to SIGGRAPH, we start working on it as a team now. That started in September of 2022. And then I guess 4 months later or 5 months, we submitted it to SIGGRAPH.
Got it. And just out of curiosity, because obviously like NeRF at the time was really dominating the world of gradients fields. Like how difficult was it to kind of depart from that to a different line of research that, you just believed in?
For me, it was very easy because I wasn't like the NeRF shop, which is excellent work with Clément Chambon, who is now, of course, at MIT. That was my first contact with NeRFs. So I wasn't really, I had worked on it in one project. So, but I wasn't super invested, right? And the field was racing along. So working outside of what everybody else was going after was actually a little, compared to what I see now, it was relatively calm, what I would say.
And so with like NeRF had that moment of like positional encoding where it just started to really like look good. Was there a specific moment in time for you that kind of was equivalent to that?
Oh, that's a great question. The quad, a few of them, but in the end, I'm not so sure that we traced them correctly, or we found the reasons, we identified the reasons for them correctly. At some point, we had this epiphany, hold on, what if we just have this opacity reset mechanic every so often? It seemed to make things better. These days, I'm not so sure anymore. We also had this, what if we just stop the densification at some key point? And that also was kind of a eureka moment where things just immediately improved the scores that we needed. But mostly it was about where can we get the performance that we need.
And then you submitted this paper to SIGGRAPH, and did you like immediately start on follow-up work, or was just like submitting and waiting?
Yeah, of course. Of course. No. So George had a very good, like he has great intuition. He has tons of experience and he has a great view of the field. And George was convinced from the beginning that this will, that like he was very certain that this will be very well received. So he had no doubt about it. So he basically said, yeah, we can immediately start to work on what's next.
And I think you published it, or at least I hit archive, I think in late April or so, or very early May. And for that time between like April and then early August with SIGGRAPH, it seemed like everyone was still very much focused on like range field methods like NeRF. And then as soon as you won like best paper at SIGGRAPH, everything started to like shift and move really fast. Did you notice like a large influx of people starting to then reach out after SIGGRAPH, or when did it start to really catch fire for you?
Great question. Yeah, I think so. A couple of months after SIGGRAPH, maybe half a month, maybe a month after SIGGRAPH, but I don't keep track of that very well. I think that would be where things started to pop off. Yes. Yeah, I think SIGGRAPH made a huge difference in this.
So I just want to show a quick, rendering, because we've been talking so much about, but we haven't actually looked at any of the examples of what. Sorry. No, my bad. But yeah, so we can see here you're able to really get like such like strong visual fidelity and get these really amazing view dependent effects that are all rendering in real time. This is like one of the really early times where we've had like Radance fields running well into the real time rates, and so but you finished the first 3 Gaussian splatting paper, and then you mentioned you started on other papers such as Stop the Pop, which addresses some of the other, I guess, implementations of Gaussian splatting. So I wanted to see if what kind of like led to that paper.
I mean, I was always sort of surprised that more people aren't bothered by these popping artifacts as much as I am. Like when we submitted to SIGGRAPH, I was like, yeah, but what are they gonna say about these popping artifacts, right? And nobody seemed to care about them as much as I did. But something where if you change the camera settings, for instance, if you put yourself in a very extreme situation, like for instance we are, right? This is a little bit of foreshadowing, I guess. But in certain camera settings or in certain configurations, these popping artifacts can be really, really nasty. So the Stop the Pop basically solution was a very, very principled, very nice piece of engineering to, again, with a great team, right? Like the guys from TU Graz, like these guys, they really know GPUs, they really know parallel processing, high performance computing. That is just top of the line. And yeah.
And just sorry for interrupting you, but the title Stop the Pop. So did you coin the term popping, because I haven't heard it before? So what is something you guys coined, or
No,
was this not all?
I think that's a common term in real time graphics. Just when something suddenly, like you see it a lot, for instance, when you have different levels of LOD, and you go from one level of LOD to the next for a mesh, for instance, and it's just really, really obvious that you made the switch. That's commonly referred to as popping artifacts. So yeah, no, that just makes sense, I think.
There are also rumors about the title Stop the Pop. Is it about stop the pop music or something like that?
So I think the guys at Graz who worked on this have a healthy disregard for pop music. Well, like there's nothing evil in there. It's just if you have a name that pops, haha, right? It will make a little bit of a difference, or it can make a significant amount of difference because people can remember it.
Right, and I think also, remembering first from like the name itself, but in this regard too, I think it makes a huge difference on the visual fidelity too. I showed this quick example here before and after, and it really does address that like popping effect. And I guess I was wondering, yeah, if you could just like give a quick overview of like what exactly it's
Oh,
over.
sure. So it's doing two things. So first of all, we have, when you do which called visibility resolution in graphics, right? You basically resolve the order in which the primitives that you are rendering should be blended together in each pixel. And 3D Gaussian splatting does this inaccurately because it only ever has one depth value per Gaussian period. Yeah? And you can go a little bit further and you can say, well, when we render, we actually duplicate these Gaussians. We put them into little lists, and every region of the screen gets an independent list of Gaussians to work through. So actually, you need to duplicate Gaussians, right? If there's one Gaussian here that overlaps with 2 image regions, basically you already need to duplicate. So what you could do is you could at least give those 2 duplicated Gaussians 2 different depth values, right? And you can do that. And you get a better, more accurate visibility resolution as a result, but you also get like very clear artifacts at the borders, right? You have one way of rendering the Gaussians, or one order of rendering the Gaussians in one tile and another one of rendering them here. So that means at the border, you now get very visible artifacts. So the second step is to combine it with a hierarchical behavior where you say you have not only these tiles, but which have their lists, but you also have smaller subtiles within those tiles, and they also have smaller lists. And these smaller lists are so small that they can be held in memory, like a memory type that is much, much cheaper to access. So you have progressive sets of smaller image regions up until you end up with the pixel, and each of them has their own shorter and shorter lists. So basically you can say I have the full list of Gaussians here, I take the closest one right now, then I go to my subtile, I have for this a separate list. I find out in this subtile what is my best estimate for the depth value that this Gaussian should have. In this subtile, you update the list of Gaussians that you have for the subtile. You take the current winner again, move on, put it into the list of the next smaller subtile. You repeat the same process until you end up at the pixel level, and you have a choice of like 2 Gaussians that you can now pick and process, basically add to the pixel. And yeah, that's basically it. Just to note, this process still isn't perfect, right? Because these lists aren't of infinite length. So the process can still make mistakes, but the mistakes are luckily like so small and significantly reduced that is a significant improvement compared to the original.
Yeah, I'm surprised because if you look at the rasterizers which are out there, like commercial ones and also open source ones, basically none of them implements this technique right now or something else, which is very surprising. It's kind of goes, maybe it doesn't disturb people that much, or just, I don't know why it's not picked up.
So I think that the guys in Graz, they know what they're doing, right? So it's not super trivial, first of all, to implement this, and it's not 100% portable. So you need certain instructions that maybe, for instance, mobile GPUs and so on might not have. So it's something that requires not a big one, but it requires some base level of hardware capability, and also then it requires a good level of software engineering ability as well to make that work.
But in the chronological order, let's go a little bit back. After the 3D.js paper, what was the next work you've been working on?
That was right. The one that followed directly was the hierarchical Gaussian representation.
Because it was like the dream of...
Yeah, exactly. With this, basically, he could do what he always wanted to do. Basically, he himself, the path that goes through Nice, I don't know, maybe we have that video somewhere. The path that goes through this long track along Nice. That's basically that's the Inria campus. That's also nice. But the one where they're going through this long track through the city of Nice, and that's actually him riding his bicycle. So he himself recorded this data set wearing that cool helmet that we show off in the paper as well, and riding around Nice and turning around at some point. And yeah, so the thing that we see right here, that's the Inria campus. And there we had one of the authors, that was Alexandre, who was walking around with the same hat on and checking out all the places of the Inria campus in East.
And did you know, like, going into this, that it just was going to work? Like, that something on this scale was just completely...
No. So the data collection and figuring out what kind of data works and doesn't work was a huge challenge there. I think we spent more time on figuring out the data and what can and can't work than on the actual approach. So, but that's I'm told that's always the case when you go for these projects that are just large scale. And that's why it hasn't been done so many times, even with NeRF. Like with NeRF, there was block NeRF, and there were a few other approaches like Giga NeRF, but many of them switch to the aerial view, right? If they say, oh, large scale, they basically mean, yeah, we have drone images from up top, yeah? But foot level or ground level exploration of vast data set, I think BlockNerf is one of the few who actually succeeded in that, because getting the data and data that works is really, really nasty. So yeah.
Right, and BlockNerf, I think, came out of Waymo with Matt Tan.
Right.
Believe.
Yes.
So I guess it was helpful with all the dash cam or other car data footage.
Yeah. And also the fact that everything takes so long. Yeah. How will you know that something has worked? You wait a week. That's just that to me is like way too long.
One of the things that I also wanted to kind of highlight when it comes to both large scale as well as the original implementation of 3DGS is that you're reconstructing this scene with potentially hundreds of thousands to millions of individual Gaussians. And with this original implementation, like the file size that you would get out of it was quite large, ranging anywhere from like several hundred megabytes to gigabyte and a half or so. And that uh since then, there's been a tremendous amount of like both compression work as well as like densification methods too that have really cut down on the number of Gaussians to still get the same level of fidelity. And so it seems like that is that kind of what led to the work of taming 3D-GS for you.
So taming 3D-GS, the motivation for this one was basically pretty much in the name, just making sure things are controllable. So yeah, we've seen these kinds of approaches which are trying to cut down, for instance, the size by, let's say, 10x, right? We want to have the file sizes to be 10x, 20x smaller. But what does x mean? That to me was always a little bit bothersome. You wouldn't bother, yeah, okay, I have a reduction of like 10 times, but what do I start out with? And all of these relative reductions sort of weren't like not very satisfactory, because you might be in a situation where you say, I have exactly 500 megabytes to spare. What is the best thing that I could get, right? Or I need to produce a model that has exactly 5,192 Gaussians, because that's the dimension of my downstream neural network into which I want to feed it. Yeah? And all of these things you basically had zero control over. So that was the main idea behind taming 3D-GS, basically making it controllable and freely usable.
And you were still able to really get like the same level of visual fidelity though in the end, while really like dropping the time.
Right. Yeah. So that's where very bright and gifted student from Carnegie Mellon University, that's Sashwat Malik, who was also part of this, we presented this in SIGGRAPH Asia this year. And basically he came up with a very nice scoring methodology for actually figuring out which of the Gaussians should be densified and when. And it just avoids a lot of the redundancy that was there in the original approach and replaces it with just like quite principled, well-informed decisions of where to put actually new Gaussians in the densification process. And then you combine that with the awesome work by Rahul Goel, who made very cool optimizations and very detailed and tough optimizations to the whole process. And because of these two combined features, basically we get the speed up of about like 5 to 6 times reduction in training, in addition to it being like completely controllable.
So given all your work in this field, what do you think is basically the success or the secret sauce of Gaussian splatting that makes it so successful for in comparison to nerves?
So I think it's an all-rounder, in so much as you can do a lot with the representation. It's very explicit. If you want to compress something and you know its points with certain attributes, you can rely on tons of previous literature to do that and apply that. So, and you can, of course, then also extend it. So it's very explicit, and it lends itself to many approaches that we already know from established computer science literature. The other thing is that it is very fast, right? So it has really nice real-time rendering performances, especially rendering performances. So it gives a lot of a performance boost to people who need to iterate quickly. But then also it's quite portable. So this is something that we showed, I think, in our 3DV tutorial, is that it is somewhat straightforward to actually make not a software rasterizer, but any hardware that you have, for instance, in your mobile device, render a 3D Gaussian splatting scene. It's comparably straightforward. So it lends itself to all kinds of improvements and extensions. It's high performance, it's good quality, and it is also portable. So I think ticking those 4 boxes makes it so that everybody can find something about it, and it basically keeps on living and finding. In each case, one of these directions is something that people are exploiting.
And did you expect that it's gonna be such a success? So was it something you have foreseen in any chance beforehand, before the publication, or maybe even a couple of months after the publication?
No. I mean, I knew that it was gonna be the most impactful thing that I had done up until this point, but no idea that it would get the kind of attention that it's getting right now.
And I guess as a result of that, has like your life like changed in any way because of its success?
I would think so. So, I mean, I have been looking for next steps in my career, right? Like, for instance, faculty positions. And after 3D Gaussian splatting, things like talking to people, making connections, learning about opportunities, and making an impression have become easier.
We didn't really even like discuss even at like a high level yet as like how Gaussian splatting like works, or like how would you describe it to someone?
I would say you have something that you want to preserve for longer time and maybe to interact with. Like, let's say, making a 3D memory of a certain moment in time, or making a 3D memory or a 3D imprint, a digital twin of something that you have right in front of you, and all you are equipped with or armed with is a camera, like a standard grade camera. And then 3D Gaussian splatting basically is a way to both find out what is a nice way to model what you have on your images. Like, from the images, a good representation of the actual 3D object itself, filling in the gaps that you don't see from the images, because you can only take so many images, right? Which means that you will always be missing some part of the object you are filming or photographing. 3D Gaussian splatting is trying to fill in those gaps as best as it can. And then, in addition to being able to construct this 3D representation, which you can now look at from any view or any position that you want to, um, it also allows you to do this viewing really fast. That's the second thing that sets it apart from what was there before 3D Gaussian splatting arrived, is when you say, I want to look at this 3D memory from a particular point of view, it doesn't take a minute until you get that new view that you haven't seen before, but it's like 60 frames per second, like the update rate of any casual real-time game that you might be playing.
Maybe let's talk for a moment about the spherical harmonics and the role within this process, because they have a nice effect, but they are also quite heavy in this process.
Absolutely, yeah.
How would you describe this? Something you would foresee which might solve this problem? Is it something we basically have to live with for a while? Or is it like, yeah, is there something maybe in the future coming up which might help to at least remedy the memory requirements?
Right. So there's not much keeping anybody from, let's say, for instance, replacing the spherical harmonics with other solutions that are out there. Like, for instance, spatially encoded color. Like, for instance, using a hash grid to store only the color information, like in a Gaussian independent, like 3D continuous encoding, something that you could absolutely do, and that the color is just taken from that. Or straight up just replacing the evaluation of spherical harmonics with a small neural network. That can also be done. Also extending the spherical harmonics with additional primitives, like, for instance, spherical harmonics plus spherical Gaussians, which some previous work has actually shown to work quite well. I forget which paper that was, so shame on me. But there was at least one paper recently that tried that mix, and it worked really well. So the spherical harmonics are definitely nice. I'm not sure right now how much of the higher bands, it's a little bit iffy what they are exactly doing, because 3D Gaussian splatting tends to create some of these view dependent effects through other means than the spherical harmonics. So they definitely have an impact, and those higher bands are definitely helping with the quality. How much and how principled it is, and what is actually the payoff, the return on investment per spherical harmonics band, I'm not sure I fully understand it yet, or what is the best solution out there. But it's very easy to, and people have done it, to go ahead and replace it, extend it, and yeah. Um, so in terms of compression, there's tons of works already out there which taking explicitly a look at the spherical harmonics band, like for instance the reducing the memory footprint paper, which very explicitly selects only the bands that actually matter. So yeah.
Hmm. And so you talk about like Gaussian splatting being a way to say like step back into a moment in time, or document a moment in time. Have you been like following along with other people who have just been like posting either like people or well production sites? Like what has that been like for you?
So I've seen, so that's actually a very super interesting, because we were looking at these standard data sets that everybody was using, which are of like outside garden scenes, monuments, rooms, and we never looked at people, and we never looked at animals. And then somebody came up and said, "Hey, what the heck? If I do 3D Gaussian splatting on my plush teddy bear, it actually works amazingly well. Or if I capture a person which has actually hair, look, here's what NeRF can do, and here's what 3D Gaussian splatting can do." And we were completely surprised by this. But we never considered this. But in the end, it makes perfect sense that it can do these fine high frequency details really well. So yeah, we followed along, and we were sort of surprised by all the things that people found when they were able to try it out from the code base that we hosted.
Do you also do your own captures?
No, sorry, no. I'm not. I'm not actually a big 3D Gaussian splatting. Yeah, no. I'm in academia. I need to always be thinking about what could be the next nice thing for the students that I supervise, and how they could have their own projects succeed in one way or another. So yeah, no, I I don't think I've gone out and taken a single. No, that's not true. I've taken some data sets for the hierarchical 3D Gaussian splatting work, but again, purely project related.
And I do want to ask, because it seems like a lot of people just in the world associate the words like radiance fields with neural radiance fields as being just like a NeRF. In your opinion, is Gaussian splatting also like a radiance field representation, or what does that like word like mean to you?
So if you had asked me like half a year ago, I would have said yes. Yet now, if you ask me now, I would say it depends. So it definitely builds on a lot of the theory that is, or basically motivates what radiance fields are. So it definitely is. The intention was definitely to have a radiance field representation, and it is also described as such in the original submission. Whether it's still fully 100% technically correct to call it a radiance field, that's a very subtle discussion that we can have. But I think for all intents and purposes, we could say yes. Yeah. For 99.5% of the people out there, if we call it the radiance field, I think that is the closest to the truth.
So from your perspective, what are the current biggest pain points in this approach? And also, what do you think should be solved to make it, I don't know, more successful? Maybe also something which might be used in the gaming industry?
So far, at least for the vanilla 3D Gaussian splatting, and this is already slightly outdated by sort of experimental approaches that I've seen in the last couple of days, is you right now have to go this way of reconstructing from images. So directly, for instance, taking your mesh and converting it to 3D Gaussian splats, that there's no pipeline for that there. But there was some work that I forgot the name, unfortunately, happening in the last few days, or coming out in the last few days, where you can actually directly take meshes, convert them to their representation, which is building and extending and modifying things on top of 3D Gaussian splatting ideas. And yes, so that makes it much more usable. You now have a very unified pipeline for 3D game engines. Many is there anything else that's preventing us from using them in 3D games? I don't think so. No. I think that loop is pretty much closed. What else is nasty about 3D Gaussian splatting is maybe still this somewhat not very principled answer to the densification question, like where do you put Gaussians? But there also we see some great work, like for instance that by Andrea Tagliasacci and colleagues. I think I'm not sure who was the first author on that. I just know that Andrea worked on it, which was called the Markov chain Monte Carlo 3D Gaussian splatting idea, which are taking a very nice approach to the densification. Let me quickly look up who that was, so that I'm giving proper credit here, right? The one that I see here is Shakiba Keratmand.
Yeah, I think that's right.
Yeah, Shakiba Keratmand. Yeah, under Kwang Mu Yi. So Shakiba from the University of British Columbia. So really nice work. And this MCMC, this whole MCMC work, like really impressive also in terms of the quality that they can get. And yeah, really nice results.
What do you think about the large scale Gaussians? Because you were like the first one who did the approach, do it in a large scale. Do you think something like this might be an approach which will get more traction in the future, like ideas to replace something like Google Maps by Gaussian representations in a real large scale? Is this feasible? Because then at a certain point you will get so many points, right? And it's going to be hard.
I mean, we were strictly speaking not the first. So even before we had even though we started working on it immediately, right? And we worked towards this hierarchical Gaussian representations, there were others before us, or slightly before us, like for instance, Octree.GS, and I'm not even sure, Vast Gaussians. I think Vast Gaussians was again aerial images, but people were looking at how can we do really large data sets and basically introduce something that is called level of detail. And level of detail is a very well established concept in real-time graphics, because people have been worrying about I have my digital world, which is thousands of kilometers long. How can I ever render that in real time? And once you have a level of detail solution, basically this problem of scalability is pretty much solved. You just need a place to store the whole data, which can be your hard disk or maybe even a remote server. And then you just need the mechanism to figure out, okay, what level of detail do I need right now from where? And how can I find it? Basically, how can I index into my larger data structure to retrieve exactly that detail at this point, get different levels of detail, which is usually a consistent amount of overall primitives. Like say, for instance, I need 2 million primitives at each point in time to get a nice image. I find those 2 million and I make sure I have them available. And whenever the player moves somebody else, some of them are basically evoked from in on-device memory, and some others are streamed in. And as soon as you have that, basically nothing stops you from rendering almost infinitely large scenes.
Sure, but you still have the problem with training such large scenes. For instance, if you are
Yeah.
another like say like Switzerland here or Austria, what in the whole country, it's gonna be really hard to train a scene, right? Because I mean, you can bring up the compute, but still connecting all the parts, it's gonna be very challenging.
Yeah, so that's why we in the hierarchical 3D Gaussian splatting, we went for a divide and conquer approach, where basically you say, well, at some point you basically make a cut between those connecting contiguous regions, and you basically treat them almost independently. And at the end, when you put all of them together, basically just make sure that everybody mostly agrees with what their neighbor has, right? That there are no weird discrepancies just at the corner. You basically get rid of that, and that way you get something that is divide and conquer, independently processable, and more easily handleable. Right. So this is again a page out of the block NeRF solution, because they made just one block is one of these independent regions, and they are basically able to also train those independently. So you get one NeRF per block is what they have. So this is again something that's just very sensible, and divide and conquer is a powerful concept.
With that in mind, then, like, what do you think are like some of the more exciting directions of this technology?
Right. So something that I've been following somewhat closely are the feed-forward Gaussian models that are now coming out, which are basically saying, well, let's do away with all of this optimization nonsense, right? Let's just take our images and let's just immediately predict all the Gaussians that we need, like in 0.3 or 0.03 seconds, directly via the transformer architecture. And there's different ways of doing that. For instance, you have the work that is Pixel Splat, which has been making quite a name, where you use epipolar attention, so a nice 3D and projection-oriented prior to actually make this prediction for the Gaussians. There's other works which are saying all you need is basically attention, exhaustive attention, right? You put attention on it, and you actually get object-level Gaussian reconstructions, which are super nice and no need for any epipolar or 3D priors. And then there's also people who are combining this with the lessons from the Mamba architecture. I think this is called, this is a paper called Long LRM, which says, oh, you have up to 32 images, you feed them into the transformer all at once, and because it's a Mamba-like system or a Mamba-like component-based architecture, you actually don't have quadratic complexity, but you have a much faster complexity, and you can again take all of these images and predict Gaussians from it directly. And what's also exciting is, of course, what's exciting is being able to take all these images and put them into one transformer and getting out the prediction immediately. But also, for instance, taking sparser views, single image views, like single image data sets or few shot image data sets, and then using generative AI to fill in the gaps so that it really remains 3D consistent when you switch to a new test view. But there I am less firm on the current state of research.
Let me follow up with one more question to the densification. Do you think this is something like directly generating Gaussians, which will replace the optimization process in the future eventually? Or is this something which will stay along with the traditional optimization-based approach? Because I think currently the quality is not yet there.
Yeah, so as long as it makes sense, I think working with optimization. So something that we learned from the 3D Gaussian splatting is if you stay true to the things you can mentally follow and comprehend, you get the benefit at the end of it, right? And people can appreciate it. This is what we saw. We basically had this 3D Gaussian splatting, which is the explicit representation, versus NeRF, which is the more implicit representation, which is sort of more of a black box behavior. And basically by using something that is very easy to mentally comprehend and follow, and basically derive from first principles, had its benefits in it being usable. And I think a similar thing applies to the optimization, at least for a little while longer, where you say this is actually the result of optimization. Like it's clear those were the inputs and that is what it derived, like only from these images. There's nothing that was there's nothing that I forget what the word is when the neural networks basically are making up things. What's the word?
Hallucination.
Yes, exactly. Sorry. There's nothing that's being hallucinated. Everything basically comes from data, right? And I think there's definite benefit for that, especially in real world use cases or in professional use cases for, let's say, surveying, reconstruction, preservation of actual historical monuments, you don't want to hallucinate details there, right? You want to stay true to the actual data. You want to derive only what the data gives you. So I think there's very much still, there will always be benefits in these principled approaches. But I would also be very excited to see have a pipeline that gives you high quality, credible results immediately. Of course, for me, that would be the most exciting to see.
And for the optimization-based approach, do you think we have on current hardware squeeze out all the performance, or is there still a gap where we can maybe get another X2 a 2x improvement? Because I think yesterday or 2 days ago was another paper which also tremendously speed up the entire optimization process. But so what do you think? Where's the limit?
So I think that the 3D Gaussian splatting method it works well, but also the design, there's so many things in there that still warrant further inspection and improvement and looking at things. If you ever pull up the remote viewer, the one that actually lets you look into the training process, you can see how random and sort of not well behaved the early stages of optimization are. So I think that being smart about this and exploiting more knowledge of scenes, not for hallucinating details, but for guiding what needs to happen when and at which speeds, I think there's still significant potential for making things converge to optimal quality significantly faster.
Also, another thing I noticed over the last weeks or months is that many people are trying really hard to get rid of the splatting itself, right? To be have more exact projection, especially within the rasterizer phase, or maybe also applying a ray tracing approach.
Sure.
Do you think it's something which will dominate the current rasterizer-based implementation, in which that's just an approximation?
So I think the ray tracing is the work that was done at NVIDIA, right, for the ray tracing Gaussians, which I also saw at SIGGRAPH Asia. That was really, really nice. I think that was Nicholas Sharp, if I remember that correctly, as the first author. And this makes a ton of sense. It's just ray tracing is such a general and well understood toolbox that if you have framework that ray traces Gaussians at good performance, then immediately you can extend ray tracing renderers to make cool artistic effects and different types of light transport so much more trivially or so much more easily than you can in a rasterizer. But I think where it's always a little bit nitty-gritty and implementation details and writing different object shaders and then coding things into triangles that shouldn't be triangles and stuff. So having the support to do it with ray tracing is a really cool thing. I think much of what this ray tracing Gaussians work achieves can also still be done with a rasterizer, but with much nastier amounts of work to achieve the same thing. So this is really, really great to have. And in terms of something that we need to point out is that these ray tracing solutions implicitly also does a similar thing. It also gets rid of the popping just implicitly, right? And I think it does it 100% correctly. So both of them, I think, stop the pop, and ray tracing Gaussians visually will probably give you the same visual impression. And in the ray tracing solution, that's just a side product. Right? Just popping free visualization just falls out of all the engineering work that they put in to make this run in a 3D ray tracing setting.
Yeah, and speaking of NVIDIA as well, they actually just came out with another, I guess, tangentially follow-up work called 3D Gaussian Unscented Transform 2, which kind of brings some of those ray tracing-based effects and be able to use rasterization.
Right. Right.
Is there any work currently which surprises you the most, or which you didn't foresee that will come that from us?
Yeah, I think these feed forward Gaussians that I mentioned before, I think those were the most surprising to me. Like I totally didn't expect that it would be possible to have in sub-second time something that makes sense. But that's because my background is not in the generative AI, right? So that basically, yeah, I so it was surprising to me that this was so quickly done and so well done.
And speaking of the world of like generative AI, have you seen any of the recent companies like World Labs or Odyssey that have started to use Gaussians to like represent generative worlds?
Only at the fringes. So I've seen them pop up every now and then, but no deep dives.
So I guess kind of extending that too, a lot of companies and startups have really come out since 3D Gaussian splatting. Has it been surprising to you, or like any of these like use cases that perhaps have come across your desk been just like I wouldn't have thought that to use this use case?
Might have been a little bit neglectful that I don't follow the startup scene that much. I mean, I'm happy whenever I see something that uh, was successful and made sense and helped people launch themselves into the industrial environment successfully. But I'm not keeping track of it, to be frank.
Do you foresee that success is going like extending to the next couple of years? Is this something which we will see even more publication, because currently it's really hard to track them at all?
Yeah. I have no clue. Like I was convinced that 3D Gaussian splatting would be um, replaced like every other. Like I'm pessimistic by nature, so I assumed whenever I saw a paper that said, when many of them do, right? Many of them write, we are 2 times faster than 3D Gaussian splatting. I was like, oh, it's over. That's it, right? There's a new method, and now nobody will talk about 3D Gaussian splatting anymore. But I mean, you have to read those papers very carefully. There's sometimes a lot of exaggeration going on. So the papers should really be read very carefully and with scrutiny, and figuring out what are they actually comparing on which data set, and is that actually a fair comparison. So I hope that I am a correct uh, I'm doing research with hopefully a lot of principle, trying to make sure the numbers we get are correct within acceptable margins of errors that can always occur, that the comparisons make sense, that they are fair. And yeah, so I think that scrutiny in this regard is really, really something that should be encouraged in computer science and in research papers.
And if there's like one thing that you want like the audience to take away, whether they're like either like researchers or they just saw Gaussian splatting and are amazed by it, like what would you want to like them to take away?
If you haven't tried it yet, I think there's tons of tools out there already that give you the ability to visualize them. If anybody else is bothered by the popping artifacts, put out some demands to somebody to make a widely available or maybe super portable, maybe web-based stop-the-pop solution, or just get the stop-the-pop solution that is out there already. And yeah, if you can think about what you could do with this representation, if it just speaks to you and you understand, here are some input images and I can make my 3D experience from them, then yeah, please, by all means, go ahead. And I hope you can find some great new applications for it. But always be vigilant. And if you have the time to look at research, make sure you look at the research and you pick the method that works, that is like really sophisticated, and you give credit to the people who actually did it. Because if there's work out there that somehow gets drowned by 3D Gaussian splatting and it's just more efficient and better and higher quality, it would be a shame if it gets drowned out just because there's a hype, right? So and very much, if you have the time, stay vigilant, stay attentive on what's coming out, because it's really easy to get drowned to get swept along with the hype. So yeah.
Yeah, thank you very much for your word. I think we should wrap up because we are a little bit over time. It was a joy to talk to you, and also that you're sharing so much from your experience and the journey you had before and since the publication. I had a great time here on the podcast. Thank you very much.
Thank you guys for having me.
Yeah, no, thank you. We really appreciate your time today. And yeah, we'll be back with more episodes in the future. So if you enjoyed today's episode, please consider giving us a follow or subscribing. It would help us tremendously. So thank you so much, Bernhard. We really appreciate having you on the show, and we will be back soon.
Awesome. Thank you so much. See ya.